This is lesson 2.1. It's about limits primarily. Our objectives are all based on the big idea of limits. I can express limits symbolically using correct notation. I can estimate limits of functions, and I can determine limits of functions. My name is Alex Stalt. I'm a calculus teacher, and here's lesson 2.1. All right, first thing is limit notation. You need to understand limit notation and what that looks like. So here's limit notation. What it says is the limit as x approaches a of some function f of x equals L. And so as x gets close to a, then the y-coordinate of the function gets close to L. Notice that f of a doesn't have to be L, and actually f of a doesn't even have to exist. So if I look at kind of graphically and a little bit more formally, if I'm within some small number, and we call that small number delta, if I'm within delta of a in either direction, then I promise you that my limit, my y-coordinate, will be within some small value epsilon of that limit. So when I say close to, we get a little bit more formal sometimes in that definition. We won't in this class, but you might see somebody talk about epsilon delta proofs. And what those are is just proving that if I give you a little tiny number, you can give me a tiny number that shows if I'm within that tiny number on my x-axis, I'll be within this tiny number on my y-axis. So the first thing I asked people to do who were in class was I asked them to use technology to examine the function sine of x over x. Without even grabbing technology, you should realize that f of 0 doesn't exist, because if you plug in 0 for x, you get sine of 0 divided by 0. You can't divide by 0, so you know that that's not true. So you know that the function doesn't exist. But is there a limit as x approaches 0? And what is that limit? And how do you know? And what's the correct notation for writing this back down? So the first thing we're going to do is grab some technology and graph it. So here's Desmos. Here's a graph of sine x over x. And what I notice about this graph is that it sure looks like, as I get close to 0, it sure looks like, even though the function is undefined, it really looks like it's close to 1. I can evaluate f of 0, or try to get Desmos to evaluate f of 0, but it says undefined. But I could get around that by just getting really close to 0, and Desmos says that the y-coordinate then would be 0.999999993. And even if I go in the, choose a negative number that's close to 0, my function is going to be really, really close to 1. And Desmos even kind of gives up. If I get even closer to 1 to 0, my y-coordinate, Desmos says, well, it's basically 1. So within the error for Desmos, the y-coordinate is 1. And I feel confident that as I get close to 0, this function is approaching 1. So using technology, I just thought about that function. And so what's the correct notation for writing this down? So I could write the limit as x approaches 0 of sine of x over x equals 1. And I want this to actually be a building block that we come back to. I want you to make sure that you have that down. So that is a limit that you should know. It comes up again. So please have that one down. So we use technology to think about that limit, but we can also determine limits algebraically. And so here are some examples of ones that we could determine algebraically. So what I'd like you to do is pause the video, and I'd like you to try to determine these algebraically. So think about these particular limits and see if you can use algebra or use other skills to try to find these limits. So pause, try them, and then I'll talk through each one. Okay, so here's the first one. The limit as x approaches 4 of x minus 4 over x plus 4. If I plug a 4 in to this function, I get 4 minus 4 over 4 plus 4, which is 0 over 8. Well, there's nothing wrong with 0 over 8. I can just divide 0 divided by 8, and I get 0. So this function, x minus 4 over x plus 4, exists at 4, and it's equal to 0, and so the limit also exists and is also equal to 0. There's nothing stopping me from plugging 4 in. That should always be your first strategy. Try plugging it in. See if it works. It might work. Okay. So then the next one, I have x squared minus 4 over x minus 2, and I'm looking at the limit as x approaches 2. So I just said try plugging it in. You try plugging it in, you get 4 minus 4 over 2 minus 2, so you get 0 over 0. Well, we're not allowed to divide by 0, so this one has a problem. It's not 0 divided by 8, it's 0 divided by 0, and that's a real problem. So what we want to do is think about any factoring we can do to get around this problem. So if I look at x squared minus 4, x squared minus 4 is a quadratic, and it's also a difference of 2 squares. So I can factor that as x plus 2 times x minus 2. And when I do that, I notice that my x minus 2 divided by x minus 2 gives me 1. So now when I plug in a 2, I actually get a 4. So this limit, as x approaches 2, is 4. This function, x squared minus 4 over x minus 2, actually acts exactly like x plus 2. It acts like a straight line, except that it has a hole. It has a hole at x equals 2, and the y-coordinate of the hole is 4. Okay, so for my next one, it looks like I have a subtraction problem well, I see a rational expression on the top that's subtraction. So I'm going to want to subtract that numerator. And if I want to subtract rational expressions, they need to have a common denominator. So I'm going to work on that. So 2 over 3 plus x, if I multiply that by 3 over 3, while at the same time multiplying 2/3 by 3 plus x over 3 plus x, I'm going to have the same denominator. So I now have a common denominator, and I'm going to divide that whole thing by x. Okay, now I'm going to go ahead and multiply out my numerators here. So I have the limit as x approaches 0 of 6 over 3 times 3 plus x minus 6 plus 2x over 3 times 3 plus x all over x. Well, now it's subtraction, and I now have a common denominator, so I can just go ahead and subtract like terms. So 6 minus 6 is 0, and then no x's minus 2 x's would be negative 2x. And then in my denominator, I have 3 times 3 plus x, and then all of that is divided by x. Okay, but I'm not really dividing by x. I'm really, like, the way I divide by x, when I divide a fraction by a fraction, what I really do is multiply by the reciprocal. So I'm going to write that out. So I have negative 2x over 3 times 3 plus x times 1 over x. And that's when I notice that my x's divide to make 1. So now I can plug in 0, and I have negative 2 over 9. So this limit is negative 2 over 9. So that's another strategy. We can sometimes work a limit out by adding rational expressions or subtracting. All right. Another one. And the limit as x approaches 4. If I plug in 4, again, I get 0 over 0. So that's not going to work. But what I notice here is that I have a radical minus 2. You have seen having a denominator that looks like that, and you've figured out how to rationalize a denominator that looks like that. This is in the numerator, but really, I'm kind of stuck. So one idea is let's just try rationalizing that. Let's see what happens if we rationalize that. So you've never done this before, but that doesn't mean that you'll never do it in the future. You just haven't done it in the past. So I'm going to rationalize the numerator by multiplying by the conjugate pair. You should recognize this as something that you've done in the past, multiplying by a conjugate pair. And when I multiply by a conjugate pair, the nice thing is that the middle terms drop out. I wind up with square root of x times square root of x, which is x, and then I have minus 2 root x plus 2 root x, so that goes away, minus 4. And then I have x minus 4 over root x plus 2, which I'm not going to multiply out because I notice that my x minus 4s divide to make 1. And since my x minus 4s cancel, now I can plug in 4, and I get 1, 4. So this limit is 1/4. So that's another strategy. Rationalizing the numerator might be a strategy that you use. The last strategy that you might use is rewriting trig functions and using limits that we know. So this sure looks like sine of x over x. It's not. It looks a lot like it, but it's not it. So I don't know about you, but I don't know double angle formulas off the top of my head, but 2x is the same thing as x plus x. And I do know addition formulas. If you know double angle formulas, you can probably skip this part of the video, but since I know just addition formulas, I'm going to use that. So sine, cosine, cosine, sine. So sine x cosine x plus cosine x sine x. Oh, now I recognize that. That is the double angle formula. It's 2 times cosine x sine x. I can never remember it, but when I see it, I recognize it. So that means that I can rewrite sine of 2x as 2 cosine x sine of x. And I'll go ahead and do that. I have the limit as x approaches 0 of 2 cosine x sine x over x. And now this part looks like something that we've worked with earlier this lesson. Sine of x over x as x approaches 0 is 1. So I'm going to rewrite this a little bit. So I have limit as x approaches 0 of 2 times cosine of x times sine of x over x. And this part goes to 1. So I'm left with 2 times cosine of 0. But cosine of 0 is 1. So I'm left with 2. Okay, so that's another strategy. You might have to rewrite trig functions and recognize limits that you've seen before. All right, we're going to skip the speed problems for now and summarize what we know about limits. So first of all, we estimated limits using technology. We did that with this limit as x goes to 0 of sine x over x. We graphed it, and then we also plugged in values that were really close to 0 so that we were estimating what that limit was. Algebraically, we used limits. We found limits using factoring. So we had quadratics, and you should know how to factor a quadratic. One of the factoring methods is difference of two squares, but we have other kinds of factoring methods for quadratics. Some teachers call it the X-box method for factoring, but that might come up in order to solve these problems. I showed you how to rationalize a numerator. I showed you that sometimes you have to add rational expressions or subtract rational expressions in order to find these limits. And then we might use limits that you already know combined with maybe rewriting trig functions in different ways. So it's kind of a lot of different skills, but it's all skills that are build on things that you have done in the past.